Dear students, in today's session, we will be learning an important chapter, Semiconductor Electronics. In this chapter, we will be learning more about the semiconductor, the properties of the semiconductor, the various devices that are made on semiconductor and their uses. So, first let us learn certain terms associated with this semiconductor, that is conduction band, the valence band and the energy gap. So, in an atom there are outermost electrons which we call these electrons as valence electron, and corresponding to this valence electron there exists some energy, and for all these energy we can draw their energy level. And the energy possessed by different valence electrons are different, and that is why we get group of energy levels together, which we can represent something like this, and this set of energy level forms a band, and it is called the energy band. And the energy band corresponding to the valence electrons is called the valence band. So, electrons are in the valence band, and depending on their energy they occupy the different energy levels within the valence band. And when you provide some energy to these valence electrons, they go to the higher energy level, and the energy band corresponding to the electrons when excited is called as the conduction band. Conductivity of a conductor or a semiconductor, it depends on the availability of the electrons in the conduction band. So, valence band is either completely filled or partially filled depending on the element, whereas the conduction band is either partially filled or it is empty. For example, in the case of semiconductor at 0 Kelvin, its conductivity is 0. So, that means no electrons are available in the conduction band at 0 Kelvin. So, we have two important energy bands, one is the valence band and other is the conduction band. So, the valence band is the energy band corresponding to the valence electrons is called as the valence band, and the energy band corresponding to the conduction electrons are called as the conduction band. And there is a gap between the two energy, and that is called the forbidden energy gap, or it is called as a forbidden band, and in this gap we do not find any electrons. So, electrons are either present in the valence band or in the conduction band, but not in the gap between the two, and this gap we normally measure in terms of a unit called electron volt. Greater the energy gap, it is more difficult for the electron to move from the valence band to the conduction band, because we have to provide more energy so that the electrons from the valence band reaches the conduction band. And the conductivity of a substance depend on the number of electrons present in the conduction band. Greater the number of electrons in the conduction band, more is its conductivity, which means in the case of insulators, the availability of the electrons in the conduction band is 0, because an insulator, it does not conduct. So, therefore, these are the three types of the energies. One is energy band, one is valence band, the other is conduction band, the other is the energy gap. It is also called as the forbidden energy band. Now, whenever the electrons are present in the valence band, let us consider there is an electron in the valence band, and this is the conduction band. Whenever electrons are given energy, they go to the higher energy band, which is the conduction band, and moment the electrons are available here, those electrons are called as the conduction electrons. So, these electrons are called as the valence electron. But once the electrons leaves the valence band, it leaves a vacancy in the valence band, and that vacancy can be occupied by the electron which is getting de-excited from the conduction band to the valence band, or even the electron from the valence band also can occupy that space to form a covalent bond, and that vacancy is called the hole, which acts as the positive charge carrier. Electron is always a negative charge carrier, whereas the space which is present in the valence band is called as the hole, which acts like a positive charge. So that's why in semiconductor there are two types of charge carriers are there. One is negatively charged electron, and the other is a positively charged hole. And these holes are present only in the valence band and not in the conduction band. Now, based on this band structure, we can distinguish a conductor, a semiconductor, and an insulator. So, this is a repeatedly asked question. So, very important question from board exam point of view. So, let me draw the band structure of the conductor first. This is for the conductor, and then for semiconductor, and then for insulator. So, this is the valence band. In the case of conductor, the valence band and the conduction band, they overlap. So, this is the conduction. In the case of semiconductor, this is for conductor, this is for semiconductor, this is for insulator. In the case of semiconductor, the valence band and the conduction band are separated by an energy gap which is lesser than 3 electron volt. Whereas in the case of insulator, the valence band and the conduction band are separated by a gap which is more than 3 electron volt. So, this is the band structure of the three solids, one conductor, semiconductor, and the insulators. And we can distinguish based on this band structure. So, I am going to explain all the three with the differences. The first property, or the first point based on which we can distinguish all the three solids are, first one, the energy gap here. As they overlap, the valence band and the conduction band overlap. So, that is why the energy gap between the conduction band and the valence band is 0. So, here the energy gap is 0. Whereas, the energy gap in semiconductor between the valence band and the conduction band is lesser than 3 electron volt. So, we have a semiconductor in the purest form. One is the silicon, and that is the germanium. In germanium, this energy gap is 0.7 electron volt, whereas in silicon it is 1.1 electron volt. So, that is the energy gap in the case of semiconductor in the purest form. Then the energy gap in the case of insulator is more than 3 electron volt. For example, in diamond, which is an insulator, so the energy gap is about 6 electron volt. So, therefore, the energy gap is more. That means the non-availability of the electrons in the conduction band is mainly because of the large energy gap between the valence band and the conduction band. So, that is why no electrons are available in the conduction band, and that is why it does not conduct. So, that is why it acts as an insulator. So, this is one of the point based on which we can distinguish all the three substances. The second point, the conduction band is largely filled with electrons at temperature above 0 Kelvin. Why it is largely filled? Because the energy gap is 0. So, that is why the electrons are very easily available in the conduction band, and that is why the number of electrons in the conduction band is very large, just above 0 Kelvin. Whereas, in the case of semiconductor, above 0 Kelvin, a very small number, that is the number of electrons available is very less, a very small amount of the electrons are present in the conduction band above 0 Kelvin. Partially the electrons are available, whereas No electrons are available in the conduction band above 0 Kelvin. They possess very low resistivity or high conductivity. Since the number of electrons are more, their conductivity is high, resistivity is less. Whereas for semiconductor, their resistivity or conductivity lies between that of the conductor and the insulator, whereas in the case of insulator, the resistivity is very high and the conductivity is least or 0. So, two more differences which we can write. In the case of conductor, the charge carriers are the electrons, whereas in the case of semiconductor, there are two charge carriers are there. One is the electrons, the other is the holes, and there are no charge carriers in the case of insulators. And in the case of conductor, they possess very low resistivity because their conductivity is high. Low resistivity, here the resistivity lies between that of the conductor and the insulator, whereas for insulator, their resistivity is very high. So, these are the 5 points using which we can distinguish the conductor, the semiconductor and the insulators. So, let us consider let us talk more about the semiconductor. The semiconductors are they are tetravalent in nature. So, if I consider a germanium, it has 4 valence electrons and it forms a covalent bond with the neighboring germanium atom. It forms a covalent bond like this, and the electrons are pair of electrons are shared to form the covalent bond. So, this is the bond structure of a semiconductor. So, at 0 Kelvin, you can see all the valence. So, these are the valence electrons. So, that forms a covalent bond. All the valence electrons are they are busy forming the covalent bond, and no electrons are available in the conduction band. So, that is why a semiconductor, it acts like a perfect insulator at 0 Kelvin because of zero availability of the electron. So, therefore, at 0 Kelvin, a semiconductor is equivalent of an insulator. And above 0 Kelvin, the energy that we provide is sufficient to break few bonds like this. And when bonds break, electrons also they are set free from that. So, let us consider these are the 2 electrons which are set free. Now, where these electrons are available? These electrons are available in the conduction band. So, that is why these are conduction electrons, CE I will write, conduction electron. These are valence electrons. So, moment the electrons leaves the valence band, and when they go to the conduction band, it leaves a vacancy. And what do we call that vacancy? That vacancy is called as the holes. So, for 2 conduction electrons, we get 2 holes. That means the number of conduction electrons are always is equal to the number of holes. And in such semiconductor where the conductivity is due to both electrons as well as holes, and we call such conductors as intrinsic semiconductors. We call it as intrinsic semiconductor. Intrinsic semiconductor is a semiconductor which is in the purest form. Why do we call purest form? Because we do not add any impurities to such semiconductors. So, let us distinguish or let us discuss what are the types of the semiconductors that we can achieve purest form as well as semiconductor by adding some impurities. So, first let us go through the properties of the intrinsic semiconductor. So, first of all, it is a pure semiconductor crystal, purest form. We don't add any external atoms or any external impurities to the semiconductor. The number of free electrons and holes are equal. When we say free electrons, we are talking about the conduction electrons, so not the valence electrons. So number of conduction electrons are always is equal to the number of holes. The conductivity depends only on temperature. That means we can increase the conductivity of the semiconductor by increasing the temperature only, because there are other alternative methods also, so which we are going to learn in the next semiconductor. Conductivity is due to both electrons and the holes. Not only the electrons, but even holes also, they contribute to the conductivity. So that's why the net conductivity is more, because in addition to the electrons, holes also contribute to the conductivity. When we say conductivity, we are talking about the electrical conductivity. And conductivity is relatively very low. So since the number of electrons and the holes, their conductivity depends only on the temperature, and we have a limitation to increase the temperature, their conductivity is very low. Now, how to increase the conductivity? Because normally these devices, they are very small in size, and we cannot increase the temperature to a very large value. So there is a limitation. So therefore we have to go for an alternative way to achieve the conductivity, and the alternative method is called doping. So the method to increase the conductivity in a semiconductor is called doping. How to achieve this doping? So what exactly doping is? So doping is adding some suitable atoms to a pure semiconductor. So you take a pure semiconductor, add some suitable atoms, and then you will get an impure semiconductor. So to a pure semiconductor, if you add some suitable atoms, you will get a impure semiconductor, and when we get that impure semiconductor, we can increase the conductivity. And we can, what type of atoms, or what are the conditions under which the atoms that we have to add? So mention two necessary conditions for doping. So condition number one, the size of the dopant, that means the size of that atom, should be almost the same as that of the semiconductor atom. So that should be the one of the criteria based on which we can select the atoms. You cannot add any atoms to a semiconductor. The atoms that we add must have a size which is almost same as that of the semiconductor that we are adding. That is condition number one for doping. And condition number two, the dopant atoms that we add should not distort the crystal lattice structure. See, this semiconductor has a lattice structure, and by adding the impurity atoms, there shouldn't be any change in the lattice structure. So this is the second most important condition. So condition number one, the size of the atoms that we add must be comparable with the size of the semiconductor, and second one, by adding atoms, there shouldn't be any change in the lattice structure of the semiconductor. And since the semiconductor is tetravalent, the atoms that we add should be either trivalent or pentavalent. So this should be the condition. So semiconductor is always tetravalent. That means there are 4 valence electrons are there, and the atoms or impurity atoms which we are adding should be either trivalent impurity or pentavalent impurity. When we say pentavalent impurity, so we have example. So we have bismuth, antimony, then we have arsenic, and then we have phosphorus. So these are pentavalent. For trivalent, we have aluminium, indium, then we have gallium, and then boron. So these are example for trivalent impurities. So these are the only impurities that are suitable to a semiconductor, so that we can get an impure semiconductor. And what is the purpose of adding atoms? To increase the conductivity of a semiconductor. So then therefore the kind of the semiconductor which we achieve, that we get, is called extrinsic semiconductor. So we have purest form is called intrinsic semiconductor. Moment we add atoms, impurities, the kind of the semiconductor which we get is called as extrinsic semiconductor. So now let's compare the intrinsic semiconductor with that of the extrinsic semiconductor. Intrinsic semiconductor, it is a pure semiconductor crystal, intrinsic, whereas the extrinsic semiconductor is a impure semiconductor crystal, or you can even call it as it's a doped semiconductor which is doped is called as extrinsic semiconductor. The number of free electrons and the holes are always equal, but in the case of extrinsic semiconductor, the number of electrons and the number of holes are unequal, they are not equal. Conductivity depends only on the temperature. So in the case of extrinsic semiconductor, conductivity depends on the temperature and doping, two methods. Okay. In the case of intrinsic semiconductor, depends only on the temperature, whereas in the case of extrinsic, it depends temperature as well as the doping. Okay. Then conductivity is due to both electrons and the holes, whereas in the case of extrinsic semiconductor, the conductivity depends mainly on majority charge carriers. Majority charge carriers. What are these majority charge carriers? Majority charge carriers means either it is electrons or holes. So you'll come to know when I explain the next type of semiconductor. So it depends on the majority charge carriers, and the conductivity is low, whereas in the case of extrinsic semiconductor, the conductivity is very high, because that is the reason why we add the impurities or dopant, that's called a doping agent, are called a dopant. So this is an important question, that is distinguish between the intrinsic and extrinsic semiconductor. So now we have two types of semiconductor, one N-type semiconductor and the other is P-type semiconductor. Again you can see repeatedly asked question from the board exam point of view. So I am going to consider first a germanium in the purest form, which has 4 valence electrons, and then it forms a covalent bond with the neighboring germanium atom. So this is the intrinsic semiconductor at 0 Kelvin. Now if I add one of the impurity atom, let us consider pentavalent, that is atoms having 5 valence electrons of 5. Example, we have bismuth, we have arsenic, then we have antimony, then we have phosphorus. So let's replace one of the germanium by a pentavalent impurity. But this pentavalent has 5 valence electrons. Out of 5, 4 electrons, so they form covalent bond with the germanium, and 1 electrons is freely available, and that particular electron is available in the conduction band. So therefore now you can see right now the number of electrons is 1, which is already there available even at 0 Kelvin. So this is the structure at 0 Kelvin. Even at 0 Kelvin, there is 1 electron is available in the conduction band. That means the conductivity starts even at 0 Kelvin. and this type of semiconductor where the number of electrons are more than the number of holes. For example, if the temperature is increased and if this two bond breaks, then two more electrons are available in the conduction band and two holes are available in the valence band. So what we get to see here is the number of electrons are always more than the number of holes. So that means electrons are majority charge carriers and the holes are minority charge carriers. And majority charge carriers are available in the conduction band, the holes are available in the valence band. And conductivity is mainly due to electrons because they are more in number. It's not only due to electron, it's mainly due to electron because even the holes also they contribute to the conductivity. And when we add impurity, that impurity energy level comes closer and below the conduction band. Closer and below the conduction band. So these are the different properties associated with the N type of semiconductor. So now what happens, suppose if I take trivalent impurity. Trivalent impurity is like gallium, we have indium, then we have aluminium, and then we have boron. So if I add any of the trivalent impurities, let me replace it as indium. Trivalent impurities means, so let me draw the original structure. So in trivalent there are only 3 electrons are available, 3 valence electrons, and they form covalent bond like this. And since there are only 3 electrons, one vacancy is available, and that vacancy is available in the valence band. That vacancy is available in the valence band, where an electron can occupy from one of the germanium to this, or an electron from the conduction band can come and occupy the valence band. So therefore, at higher temperature, let me consider if these two bond breaks, then 2 more electrons are available here in the conduction band, and for which the 2 vacancies are created. Again, which means the number of holes are 3, number of electrons are 2, number of holes are more than the number of electrons. When number of electrons are more than the number of holes, the negative charge carriers are more in number compared to the positive charge carrier, and such type of semiconductor is called as N type of semiconductor. N stands for negative type, N, negative. And whenever the number of holes are more in number than the number of electrons, such type of semiconductor is called as a P type of a semiconductor. Here the majority charge carriers are the holes, the minority charge carriers are the electrons. So we can distinguish the two, and then the energy level corresponding to the impurity atoms lies closer and above the valence band. So by adding pentavalent impurities we get N type semiconductor. By adding trivalent impurities we get P type of semiconductor. So let's see the differences between these two types of semiconductor, and again an important question. The point number 1, it is obtained when a pure semiconductor is doped with pentavalent impurities. So we are talking about the N type semiconductor. So what about the P type? It is obtained when a pure semiconductor is doped with trivalent impurities. Number of free electrons is greater than the number of holes. And the next here, in the case of P type, the number of holes are greater than the number of electrons. Conductivity is mainly due to electrons here, and in this case the conductivity is mainly due to the holes. Majority charge carriers are in the conduction band. Majority charge carriers are in the conduction band because here electrons are the majority charge carriers and they are present in the conduction band. whereas in this case the majority charge carriers are present in the valence band. The donor impurity level is closer to the conduction band. So whenever we add pentavalent impurities, it donates an electron, because out of the 5 only 4 electrons can occupy covalent bond with the germanium. That means whatever that one extra electron is given by that impurity atom, that's why it is called as a donor impurity. And that donor impurity level is closer to the conduction band, closer to the conduction and below the conduction, closer and below the conduction band. Whereas whenever we add trivalent impurities, there are 3 electrons which forms a covalent bond with the neighboring germanium atom, whereas one vacancy is created which acts as hole, and that hole can accept an electron. That's why the trivalent impurity is also called as acceptor impurity. Pentavalent impurity is called as the donor impurity, and in the case of p-type semiconductor, the acceptor impurity level lies closer to the valence band. In the case of n-type, the donor impurity level lies closer and below the conduction band, whereas in the case of p-type semiconductor, the acceptor impurity level lies above and closer to the valence band. So this is the last difference between the p-type and n-type semiconductor. So I have explained the 3 important differences between 3 solids: one conductor, semiconductor and the insulator. That's an important question. After that we have discussed intrinsic and extrinsic semiconductor, another difference again which is an important question. And the next is so here we have 3 important question: distinguish between conductor, semiconductor, insulator, distinguish between extrinsic and intrinsic semiconductor, and distinguish between p-type and n-type semiconductor. So I am going to continue the rest of the topic in my next session, and this chapter, that is chapter 14, will be completed online. So therefore do watch the group, so that I am going to upload videos on almost a daily basis. Thank you.